Hello. Wait a few more minutes. So what, one more week and then everyone over the age of 16 is eligible for vaccines? Or 16 and over, I should say. I think one more week. I hear the Cal State LA is already giving them to everyone. I guess they have enough unused doses at that site that anyone 16 or over can show up. No need to show that you have pre-existing condition or work as an essential sector. They're just giving it to everyone.
Do you know which ones they are giving out? Because I know you don't get to just choose which one you get, right?
I heard a rumor about it, but who knows? The best vaccine is the one that you can get into your arm ASAP.
Yeah, that's what I was trying to argue over here at my house as well. Just any vaccine works out fine.
Yeah, I mean, I don't know. Somebody could argue the pros or cons of whichever one, but just the best shot is the one that's in your arm right now. Because there's three effects from vaccines. There's, of course, the protection for you, and some will say, well, it's not perfect. Nothing's perfect. There's the protection for the person that you're interacting with, which might prevent them from even getting it to give to you in the first place. And then there's the protection of everyone else that they interact with, because hypothetically, let's say that you're in that small percentage for whom it doesn't work so great, and the person you're talking to is in that small percentage. Well, guess what? Everyone else that person's interacting with is almost certainly in the large percentage. If they're in the large percentage, they can't give it to that person. So, in order for you to get it from someone, it has to break down for you. It has to break down for the person you're interacting with. It had to break down for the person before that. And so it's a threefold protection. Wait one more minute. Okay, so last time we were talking about the diffraction pattern of circular apertures. And I noted that if you look at the diffraction pattern of a circular aperture, like the pattern of focused light, as long as we don't have aberrations, you get something like this: a sharp central peak, and then an interference minimum, a secondary peak, another minimum, a third peak, another minimum, and so forth. That's what you get as long as you don't have aberrations. Now, what you should notice, what you should have seen on your previous assignment, is that if we widen the aperture, that slowly starts to go away. If I make this aperture wider, we don't quite get a smooth dip down there. We don't get perfect destructive interference. And that's because you can't really find a place where half the paths are positive and the other half the paths are negative. You can't really get it so that that average difference is a half a cycle because there are too many different path lengths. Everything is too smeared out. And so now you start to see the transition to the aberration limited regime. You might say, well, that still looks, I mean, it still looks fairly good. There's a dip. Yeah, there's a dip, but it's not as sharp of a dip. The loss of destructive interference is one of the indicators that you're aberration limited. The other big indicator, of course, is if you compare the spread with what the wave theory would predict, you find that the energy is spread out over a substantially larger area. Any questions on that? Now, one thing that I did not make, oops, no, that's not what I wanted to share. I want to share my screen. One thing I didn't really make clear last time because it was going around in my head, wait, how do I explain this? We started talking about what happens if you have a lens and we could run the lens in either direction. All right, we could run the light from left to right or right to left. And I said that, well, you know, it's going to get smeared out. If we image from here to there, it's going to get smeared out. Conversely, if we image from right to left, it's going to get smeared out. And I was a little bit, I was waffling on when we just say 0.6 lambda over n sine theta. And when I put in a factor of magnification. I was waffling on that because I'm looking at it, I'm like, there's got to be a way to include the magnification, but nothing's natural. There was nothing that was naturally jumping out at me and saying, oh, here's where the magnification is. Well, that was dumb on my part. We call this theta 2 and we call this theta 1. And this side, the spot size, will be 0.6 lambda over n sine theta 2. On this side, it'll be 0.6 lambda over n sine theta 1. Which spot size is bigger? Just based on those equations. If it helps, assume that n is the same on both sides. As a matter of fact, if it helps, assume n is 1, so we don't even have to include it. And lambda must be the same. You know, it's the same light source either way. I know I drew one of them red and one of them blue. That was just to differentiate which way we're going. Which light source, which spot size is bigger? 0.6 lambda over sine theta 1 or 0.6 lambda over sine theta 2? Why is the spot size on the right bigger? Someone said in the chat. Okay. What's the reasoning for that answer?
Is it because theta 2 is smaller than theta 1? And since it's in the denominator, it ends up making the whole thing bigger?
Yep, we've got a small denominator here. We've got a big denominator there. All right, and so the magnification is already baked in. Okay, because at least in the paraxial approximation, the magnification is already baked in. In the non-paraxial limit, everything is more complicated. But in the paraxial limit, the magnification is baked in. As long as these angles are small, then we could replace theta with, well, if these are small angles, I'll call this R. Sine theta 2 is roughly tan theta 2 is equal to R over S2. Sine theta 1 is roughly tan theta 1 is roughly R over S1. And so spot size 2 over spot size 1 is equal to, well, let's see here, 0.6 lambda over sine theta 2, and then 1 over sine theta 1 is sine theta 1 over 0.6 lambda, cross out, and we've got R over S1 time for sine theta 1 times S2 over R, cross out, S2 over S1. Any questions? Okay, now, one point I made is that this pattern here, this cross-section pattern, at least in the diffraction limited regime, do a quick focus to make it a little bit sharper. This pattern, which is called an Airy function, it's based on Bessel functions, and we see it plotted. Oh wait, I didn't share my other screen. Sorry. Yeah. Okay. So this pattern is based on something called a Bessel function. Looks like this, but Bessel functions are messy to deal with. E to the minus x squared or e to the minus r squared or whatever times some constants. That's actually much easier. And it turns out that we can approximate this. I'll magnify all of this. It turns out that if we just play with, we write it as e to the minus k squared r squared times some constant alpha. And if you just play with it, somewhere around 0.27, give or take, is about the best value of alpha. It actually depends on how you want to measure the agreement, but no matter how you measure the agreement, any reasonable definition of match between those two gives something around 0.27. Believe it or not, there's actually been a bunch of papers published on that question because it was a technical issue that mattered for doing some types of work to maximum precision. But we're going to just run with that, because if we just run with that, then we can do our math much more easily. Calculations are much easier to do. And you might say, well, that still seems kind of like a cheat. Not really, because let's consider what happens if we make this aperture pretty big. That doesn't look so great. Let me just check something in the layout. Yeah, it completely fills it. So we're missing some stuff. Let me widen the mechanical semi-diameter here. I should widen the clear and mechanical. Oh, no, can't widen it that much. What was I thinking? So I will make this thicker. I will make it thicker still so we don't have these issues. Layout. Okay. If I widen it that much and do a quick focus, you might say it doesn't really look like a Gaussian because it's got all of those. Well, we'll get rid of some of those. at least to some extent. It's hard to completely get rid of them. But here we are way far into the aberration limited regime. Enough of that. Here's what matters. Here's what matters. What matters is that it's a good enough approximation in any of these cases that people have won Nobel Prizes for work that approximated the point spread function with a Gaussian. So we're going to approximate it with a Gaussian. And the usual way that they write it, there's two ways. Either they write it as 0.27 e to the minus 0.27 times k squared times r squared, or they write it as e to the minus 1/2 x minus x naught squared over a width squared. And there is a reason why they do that, which is that if I write it like that and integrate it, yeah, it starts getting nitpicky with me. Says, well, how do you know that w squared is positive? All right. The reason I can do that is the square root of 2 times pi times w. Sorry. The reason is quite simple. If I write it like this, the area under the curve is 1. It's a very convenient approximation so that that little constant out front is telling us the area under the curve is just equal to that little constant a out front. Now let's see what happens when we play with this. All right, so we've got a graph, and we're going to see how these parameters affect the shape. The x naught moves it left and right. The amplitude out front just determines how tall or short it is. And w determines how wide it is. The way to think about it is that, all right, we've got x minus x naught squared in the exponent. If x equals x naught, then x minus x naught is 0. And so you just got e to the minus 0, which is 1. If x isn't x naught, well, then x minus x naught is non-zero. We square it, we get something positive. We multiply by minus 0.5 and divide by w squared. We've still got something, now we've got something negative. We've got e to the minus something. And e to the minus something is going to be less than 1. So over here, e to the minus all that mess is 1. Over here, e to the minus all that mess is less than 1. Here it's even less than that. And likewise here. Here it's less than 1. Here it's even smaller still. So that parameter x naught determines where the peak is. W, well, we're dividing the exponent by w squared. And so if w is really big, then we're dividing the exponent by the square of a big number. So we get a tiny exponent. E to anything negative is less than 1, but e to the minus 0.1 is pretty close to 1. E to the minus 100 is almost 0. And so the bigger W is, the smaller the exponent is. Sorry, the bigger W is, the smaller the exponent is, and so it spreads out more. Okay, it takes longer for that exponent to get to be a really big negative number. Any questions on this? Okay, well, let's say we have 2-point objects, all right? Each of them produces an image on the camera. You know, the lens focuses the light, and the light gets focused to a spot of some finite size, and it has a shape like this. So we're going to just fix the height. We'll make them both the same brightness. Now, if the objects are really far apart, their images are also really far apart. So you could look at it, you could say, all right, there's a bright spot here, there's a bright spot there. And taking pictures of point objects, you might think, well, in reality, do people take pictures of point objects? First of all, yes, they do in biology. In biology, a fluorescently labeled molecule is a molecule that has something attached to it that glows really, really bright. Well, the thing attached to it is essentially a point. It's way tinier than the wavelength of light. Second, we could think of any real object as being composed of a bunch of points, and the camera is basically forming images of each of those points. And well, if the points are far apart, the images don't overlap. But if the distance between them is small, they start to overlap. Here, they're just barely overlapping. You could still see that there's two things. But here, they're strongly overlapping. Now let's look at what we're really plotting here. We've got object 1 in blue. We've got object 2 in orange. And their combined image is green. You know, the camera doesn't get to say, oh, this light is from object 1. I'm going to count that separate. And that light is from object 2. I'm going to count that separate. The camera doesn't get to do that. The camera just says, well, right here, I've got this much light. Hey, maybe some of it was from one object. Maybe some of it was from another, whatever. This is the amount of light I've got. And so as we bring them closer, if they're right here, you can still see a little bit of a dip, and you can say, all right, well, it's brighter here and here and not so bright there. So this is probably two separate objects. But once I bring them this close, well, now it just looks like one rather wide image. You might say, huh, that's a little bit wider than I would expect something to be. It's probably more complicated than one point, but you wouldn't be able to easily look at it and figure out what it really is. There are mathematical techniques that could do that sometimes, but those techniques have a lot of limitations to them. These techniques are far from perfect. And if you just say, oh, machine learning, well, even machine learning, garbage in, garbage out. It would depend on how much signal to noise there is. Machine learning can't look at a noisy image with no real signal in it and say, ha, I found something. Well, you can say it, doesn't mean it's right. So the key thing to take away is that the closer they are, the more they overlap, the harder it's going to be able to tell what's really going on. Here you'd have no idea that there are, or probably have no idea that there are two distinct objects. Here you would certainly have no idea. And here, well, who knows? Someone must have a question on that. This is the whole idea behind the limited resolution of a camera or any lens. A lens really cannot distinguish two things if the separation between them is more than the width of the image that the individual points form, okay? We call this a point spread function. This Gaussian here, or this Airy function, and for some kinds of lenses, it's something else entirely. It's called a point spread function because it's telling you just how much the image of a point got spread out. That's literally what a point spread function is. Take a picture of a point object, and instead of getting all of your light in one tiny little infinitesimal region of the detector, the light gets spread out because the lens diffracts. It might also have aberrations, but the light spreads out over some area. How much it spreads out? Well, that depends. What's the shape of that spread out image? That's called a point spread function. Somebody must have a question. This is what the whole idea of the Rayleigh criterion is, or the Abbey limit. I said on Tuesday that Ernst Abbey worked out the size of the blur, the size of that little diffraction limited image, like right there, worked out the size of this thing. All right. I said that's the Abbey limit to resolution. Rayleigh worked out something analogous for telescopes, and that's the Rayleigh criterion. It all comes down to a very simple question. If I'm looking at two different objects, how close together can they get before their images start to overlap? It's somewhere around there. People can argue over exactly, well, should it be here, or maybe out to there? You can have different criteria. But qualitatively, once you start to see some significant overlap between the tails, you can't look at it and clearly tell that there are two distinct objects. Somebody must have a question on this.
Professor, I have a question. I was writing it down, but so you said a lens cannot distinguish two objects that are over one width of the individual object?
Well, a lens can't distinguish anything. A lens, unlike some humans, doesn't have a brain. But a human or a computer cannot really distinguish two objects in an image made by a lens if the images are closer than the width of that point spread function. However wide or narrow that point spread function is, that determines how close the images can get before they start to overlap.
Okay, so I was wondering if you could like provide us like an example of that, like in real life, I guess, like a scenario.
Okay, so let's say that I'll start drawing on my other device. Lens, optic axis, two fluorescent molecules. Okay. Each of those fluorescent molecules produces an image way on the other side of this lens. And one of the images will be right here, and it'll look like that. And the other image will be maybe right here. Now we would say these two fluorescent molecules are far enough apart that I could see that there is one whose image forms there and one whose image forms there. And I could work backwards using the magnification to figure out how close together they were in the specimen that I'm looking at. And people routinely tag things with fluorescent molecules in biology. They basically come up with a molecule that satisfies two criteria. One, it glows. Lots of things glow. 3 criteria. 2, it attaches to the part of the cell that you want to look at. Lots of things attach to the part of the cell you want to look at. 3, doesn't attach to many other things. And doesn't hurt the cell or damage it, or if you're okay with killing the cell, great, but at least it doesn't mess up anything else that will make it hard for you to look at and see what you want to see. Those are the 3 criteria that have to be satisfied. All right. So in this case, we would say, well, these two images are separated by more than the width of the point spread function. Let's say,
Huh.
I see
Oh.
it has just joined us.
That's pretty fun.
The kid has joined us. I hope you're having fun hearing about optics. So now let's say that we look at a third molecule, which is right between them.
Purple ball.
I don't know.
As much as I like kids, you know, a few comments are great, but if someone could mute their
Send it to
microphone.
couch.
I think it went under the couch.
Andrew, is that you?
I found it.
Oh, sorry.
That's okay. The little kid is
I have a
cute.
little brother next to me.
Oh, little brother. Hi, Andrew's brother. Okay. So now in this case, we're looking at a third molecule seen between them. Well, now we have a problem because I've drawn them in red and blue just to make them distinguishable to our eyes, but presumably they're emitting the same color. These 3 images overlap. So what you would probably see is something that looks like, maybe there'd be a little bit of a dip there and a little bit of a dip, but something that looks like that. So it would be much more smeared out. You'd never be able to see what's really going on. Does that help?
Yeah, that helps a lot. Thank you.
Okay. So, like I said, we call this shape a point spread function. And the PSF is equal to I naught times e to the minus x minus x naught squared plus y minus y naught squared over 4w squared. All right, and what that tells you is that if x and x naught and y naught are the position of the point source, and x and y are the position where we detect light. So I could figure out, given the coordinates of the molecule, I could find out how much light was falling on every point on this image. All right.
Professor, what's in the denominator of the?
4w squared.
Okay, thank you.
Sorry, the diagram got busy there. All right, so again, draw my optic axis, my lens, an object here. We'll just for now do one-dimensional problems. So we've got points here, here, and here. They form images that all have the same shape. It's just that each of them, one of them, we've just got e to the minus y squared over 4w squared. And here, well, the image should be at, let's say this is y equals -3, And then down here is y equals -6. And this was y equals 0. I should be saying y naught. E to the minus y plus 3 squared over 4w squared. And finally, e to the minus y plus 6 squared over 4w squared. So those would be the images that each of them form. And they're all just the same shape. Pretend that I was able to draw consistently. They're all the same shape, just centered at different places. And so we would say that the intensity in the image plane is the sum over objects. We'll label them I equals 1, 2, 3. I'll call this I sub I brightness, because maybe one of them is brighter than the others, times the PSF of x minus xi, y minus yi. Any questions? It all just comes down to adding up the same function with possibly different brightnesses centered at different points. No other questions? All right, one thing I want to talk about is what happens when things are out of focus, because there's no guarantee that our lens is perfect, that our image is perfectly focused, that our lens has been set up so that our image is perfectly focused. I mean, ideally, whoops, wrong there. Ideally, of course, let's say that we do have pretty good lens. But for one reason or another, we don't have everything perfectly in focus. And that can happen for a lot of reasons. Even if we set everything up perfectly, it could be that we actually focused on a slightly different object. Maybe we focused on an object here, or let's put it there. We focused on this object because this was more important to us for whatever reason. Well, if the object is closer to the lens, then where should the image be? We move the object a little bit closer, where will the image be? Closer or farther?
Further away.
Further away, yep. So maybe we originally focused on this image. And then we want to say, okay, what about this object here in this image? Well, we know from the things we did in the first half of the semester that the light will be spread out. But the question is, how will it be spread out? And we know that our theory of how the light spreads out can't be perfect, because here, the stuff we learned at the beginning of the semester would say that if we had a really good lens, this width might be 0. But we know that can't be the case. It can't be 0. So it turns out that it actually spreads out like this. It spreads out in such a way that initially, I'm just drawing the edge of it. Initially, geometrical optics is a pretty good approximation. sticking pretty close to what geometrical optics would predict. But as it gets near the focus, it doesn't remain like that. The width is non-zero in wave optics. Now, think of this as the beam edge, and you could ask, well, what is the edge of the beam? I mean, it's not like the light truly goes to zero. You know, if we were to say that this is brightness or intensity, this is your off-axis distance. Ideally, we would love it if it were like this. All of the light just confined. You know, we go along here, and we measure the brightness along this line. We'd love it if it's 0, 0 over here, 0 over here, uniform there. But that's not the truth. In fact, it looks more like this. And people have various criteria for where they will, what they will call the edge. It's usually 1 over E times the max, or 1 over E squared times the max, which is just a convenient thing for doing the math. And you know, once you've gone out that far, you know it's significantly dimmer than it was on axis. That's the basic idea. So that's what this line is, this thing that I'm going to redraw in blue that starts off following the geometric path, the thing that Zmax would predict for rays, and then kind of veers off before continuing towards the geometric path again. What does the shape of that blue curve look like to you? Blue curve is a what? What's a shape that starts off following a straight line? And then as that straight line gets ready to intersect the axis, all of a sudden it kind of flattens out rather than going to the axis, and then comes back and starts heading towards the straight line again, asymptotically. Think way back to high school. Some kind of curve, not parabola, hyperbola, yes, and that's no exaggeration. It is a hyperbola, right? So if I call this distance W, the distance from the axis, that's basically the width, and I call this distance the distance from the focus, Z, then W squared over W naught squared minus Z squared over Z naught squared must be 1, because that's the definition of a hyperbola. And you could say, okay, well, what is this W naught? All right, what is this minimum width? But I think we know what that minimum width must be. If we just think back to a distant time known as Tuesday, what should that minimum width be roughly? What is the minimum spot size that we can focus light down to roughly? Think back to Tuesday. Tuesday was a long time ago. I had to give the lecture in Sanskrit because that was the dominant language during that period of the Earth's history. But think way back to Tuesday. What is the smallest spot size? You can answer in English or in Latin or Sanskrit or Sumerian if you wish.
Is it 1.2 times the wavelength divided by sine theta?
Close, it was 0.6 lambda over sine theta. Okay. And that would be the width when z equals 0, because if z equals 0, w squared over w naught squared equals 1. So w is w naught. Now, we don't yet know what z naught is, but here's something we do know. We know that as we get further away, it's almost on axis. If it's on axis, this angle theta, w, z, maybe I think of if it's right on axis, so it's basically following a line. What's the relationship between w, z, and theta?
Is it tangent?
Yep. All right, so what we know is that w over z approaches tan theta. So if w squared and z squared are huge, then w, then in reality, w over w naught is the square root of 1 plus z squared over z naught squared, just by solving this equation. And if z is huge, then z squared over z naught squared is huge. So we can leave out that 1. So it just approaches z over z naught. So w over z is w naught over z naught is equal to tan theta. Any questions? All right, so what have we worked out so far? We've started from the fact that light spreads out, doesn't focus to a perfect point. We observed that shape that it focuses down to can be approximated with a Gaussian. And then we said, okay, well, we know that far away from focus, it obeys geometrical optics. It's only right near the focus that we have to really start paying attention to wave optics, because wave optics predict that the size cannot possibly go to 0. And we looked at, well, what would that deviation have to look like? It's heading towards that point, all of a sudden it coasts away. So we get a hyperbola. We use the properties of the hyperbola. We were able to predict what z naught is, or basically how wide this region is. How wide of a region can it travel through before it gets towards the geometrical optics case. And I could try to introduce more material, but at 6 o'clock, we have one of our graduates coming to talk about her work in optical engineering. So we should probably take a break before that. And if I try to introduce more material in the next 2 minutes before a break, it won't go well. So let's just take a break now, and we'll pick up with this on Tuesday. And on Tuesday, we will talk a little more about this Gaussian approximation, and then we will talk about the modulation transfer function. So far, all I've done is work out what the point spread function is. I've worked out the shape of the point spread function. On Tuesday, we will talk about the significance of the shape. We'll talk a little more about the shape of the Gaussian point spread function, and then do modulation transfer functions. So take a break, come back at 6. Hello, Bianca. Thank you for joining us.
Hi.
When's the last time I forget, when did you graduate? Was it not 2019 or 2018?
It was 2019.
2019. So I think have you been to campus since then?
No, I don't think I have.
You couldn't have been to campus in the last year, so yeah. So you moved around a few times. I know you were doing something well, let's wait for a minute for students to come back from break, and then we'll get into your career biography and everything.
Yeah. And then also I got a black eye this past weekend, snowboarding. So we're gonna put that out there. Yep.
Okay. I can't even really see it, so.
Okay. It's in the healing phase. It happened on Saturday. So
Where did you go snowboarding?
so I live in Utah now, and I went to a Solitude, which is in Big or Little Cottonwood Canyon. I think it's Big Cottonwood Canyon. So yeah.
For some reason, I thought you were working in Orange County. I don't know why.
Wow.
Okay, well, it's 6 o'clock, so most people should be back. So we have here Bianca Cruz, who graduated from this department in 2019 and is working as an optical engineer. So why don't you start by telling us about your current job? I know that there may be some specifics about projects you can't say, but in general, what sorts of things you do as an optical engineer?
So my job, so my title is like optical engineer, but I think my duties align better with manufacturing engineer. So I help support the fiber optic gyroscope line, which is used in navigation systems. So like missile defense, aircraft vehicles, and that kind of ordeal.
I barely know what a fiber optic gyroscope is. So what is it?
Oh, it's pretty much, so I have a slide. Let me present my screen if that's okay.
Sure.
Share screen. Here we go. Cool. So let me see if I can get this. So in my little like presentation, I'll go over a little bit about myself, what we do, the project background, day-to-day tasks, and like some of like a piece of advice that I have for you all. So I was born and raised in Anaheim. I graduated in physics in 2019, and some of my favorite classes were advanced instrumentation, E&M, optics, electronics. So I really liked electromagnetic waves. And I would say my background initially was not going to be in the optics path. I was really interested in biophysics and kind of biological related fields or biomedicine. But an opportunity kind of arose in Salt Lake City, and I moved and now work at Northrop Grumman as an optical engineer. And so at our facility, we're mission systems. So like I said, I support the fiber optic gyroscope line, which is used to be built in inertial navigation systems to help navigate aircraft. So the three big product lines that we have are LN200, LN25X, and WISM 12. LN200 was used in Perseverance in the Mars rover. I think for all Mars rovers, to be quite honest. So these are mostly coils used in the space program. We have a longer coil, which is 1 kilometer, used in missile defense, and then WISM 12, which is our largest coil, which is 3 kilometers long, and it's used in Navy submarines. So these are the two big product lines. Can you see this? Is this distracting?
No, it's not distracting.
Okay. So how do fiber optic gyroscopes work? It's pretty much interference. It's literally nothing new. Essentially what happens is we have the Sagnet effect occur. So when we have a coil, so I work mostly with the 1 kilometer coils. So if we have a coil and it's stationary throughout the light's entire path, will shine light through both legs of the fiber, and they will interfere with one another. And if there's no rotation in that gyroscope, there is no optical path length difference. However, when this is placed into a system, you know, your aircraft's moving from turbulence or other environmental factors. And so your inertial frame changes as one axis of that plane rotates. And so one path will be shorter than the other. And that is a measurable phase shift that we can calculate as position.
That's a relativistic effect due to the rotation being accelerated motion and acceleration and gravity producing basically a type of Doppler shift of the wave, right?
Right.
Okay.
Yeah. So
Not something they see in their relativity class, so that's why I was saying what it is. But go on.
yeah, so like I said, they measure rotation in a specific axis. So in an aircraft, we want to be able to measure roll, pitch, and yaw. So your X, Y, and Z axes. So your gyroscopes will place 3 gyroscopes into a unit in the 3 dimensions alongside with accelerometers. And so the benefit of this is, unlike GPS, which gives you just latitude and longitude, which is just position only, inertial navigation systems will generate measurements based on their last known position. And so from your, it's pretty much like an inertial frame, and then you'll compare it I think we do every 100 hertz. And so this process of like the gyroscopes and the accelerometers working together to get position and velocity, that process is called dead reckoning. So if you want to learn a little bit more about it. So my tasks, as I said, are more in line with a manufacturing engineer. So while I support the fiber optic gyroscope production line, I also look at optical testings to investigate common failure modes. We check equipment calibration and replace all tools constantly. And we're always looking to analyze different parts of the process build to improve efficiency or the ergonomics of a process. The one little task that I do have as like an optical engineer is research and development. So there's a few projects that I'm on, and it just pretty much my task for those are material procurement, engineering drawings to send to vendors, and doing proof of concept experiments to get funding for the research. And so I kind of use ZMAX. The way that I use it is mostly as a kind of like modeling an actual experiment. So this is a bifringent crystal that we had in lab, and for one of our research projects, we wanted to know the separation distance in this bifringent crystal as soon as the light exited the crystal. And so essentially, we just got a Heaney laser, shined light through it, and measured the separation of a certain distance. I want to say it was like 2 feet away. We had a screen and then measured how far those beams were And then we modeled it onto ZMAX so that we can actually get the separation distance for one of our projects. And then my piece of advice is to take classes outside of your major. I solder a lot. I have to identify parts of a circuit board or an optics card, and kind of play around with it with different testing that we have to do. I have to procure different materials, so I have to know their physical chemistry and we do magnetic shielding and those types of things. So I really encourage people to take courses outside of their major or be involved in projects that are multidisciplinary. And then also what's been like my lifesaver is taking really detailed, clear notes. So I have a couple friends that are also at Northrop Grumman, and sometimes I'll message them and say, hey, do you remember that code that we had in applied optics where we did X, Y, and Z? Or did you ever do a lab in optics where you had to measure the extinction ratio of a polarizer? And so I kind of gather all of these lessons and kind of compile it to my day-to-day job, which will help me. I've had to build a couple interferometers, and I had to rely on some of my previous labs just to remember how I set everything up and aligned all of the light. And it's also great to have them for interviews. I remember they asked me what kind of splicer I use and kind of really specific questions that, you kind of forget after a while. And so having really detailed notes about what you used, how you used it, how it works, was really beneficial for my interviews. And then some of the takeaways, additional takeaways that I have is to practice your Python and coding skills. There's only me and one other person that code in our group. And so we're constantly getting questions and people want us to help them visualize their data. So it's really, really helpful to have that skill. I use SolidWorks all of the time because as a manufacturing engineer, we're trying to build new tools that are more ergonomic for the operator. And so I'm always sending tool requests and tool designs to the 3D printer people. And skills that I wish that I had were kind of better data mining. So we use SQL to manage and access all of our databases. And it's just a different type of coding. I'm still trying to get the hang of it, but I think most people use SQL to look at large databases. And then take more stats classes. I think you can learn on the job, which is pretty much what I did, but I think it'd just be easier if you just took stats and just had that background and help. And then when going into industry, if that's the path that you want to take, ask every single question that you can. And I say that because you are hired as the expert on that product line. And so after a year of being there, a year or two, you are the go-to person, and you're expected to know all parts of your project and be able to provide feedback and kind of, I want to say, like, protect your product, because a lot of the time they'll always say, oh, we think it's the gyroscope that's not working properly, but realistically it's probably like the hardware or the photodiode, or there's always some other hardware issue that's kind of overlooked all the time. And that's kind of like my little spiel. You can contact me, but if you have questions, throw them my way.
Who has a question for Bianca?
I do, if I may.
Go
Yeah.
for it.
Hi, Bianca. I was wondering, what were some other questions that they asked you during your interview? Because I'm actually interested in going into optics engineering. I just kind of want to get an idea of what they kind of require or ask during, if you don't mind saying.
Yeah. So my interview was kind of a little strange. They asked a lot of questions about what was on my resume. We went a little bit more in depth about, I did research in fiber optics, and so they wanted to know what kind of experiments that I did, issues that I ran into. They asked about my ZMAX background and whether we worked in sequential or non-sequential modes, which, by the way, we work in sequential. And I think my biggest advice with interviews is just be honest. I remember they asked me if I did sequential or non-sequential, and I paused and said, I have no idea what the difference is. I didn't know there was two different types or two different modes to work in ZMAX. Other questions that they asked were a little bit more like personal, more about like my characteristic, how I would handle interpersonal issues that may come up. Yeah, I think that just about covers it. They just really drill into what you write on your resume, and then they ask about how you would handle conflicts or how you would handle an issue. Another question that I remember is they asked me if they gave me a task or they wanted me to investigate a certain issue. They asked me, how would I go about it? And the way that I responded was by saying I would look into it at first, draft up kind of a plan of action, and then go to someone who's an expert in that field, check with them to see if I'm missing anything, I guess, or if they had a better way of testing that issue, and then proceed to do whatever experiment they wanted me to do.
You mentioned keeping lab reports and applied optics reports and coding for interviews. Were you asked to bring any samples with you to interviews or give presentations on them?
No, they have asked me really detailed questions about my lab reports. They have asked me, I remember there was a lab for advanced instrumentation, and they asked me what the graphs look like, what were the axes, and how did I determine if there was a phonon. I forgot which experiment that was, but they wanted me to go to the whiteboard and graph it.
Would you say that this interview format is what some of your friends who graduated recently also describe, at least roughly similar?
Yeah, I would say it's about the same.
Good, because that's what a lot of other students tell me as well. I actually was just talking to someone who is a current student, but he was interviewing for an internship yesterday, and they were asking him very, very detailed questions about what Python packages he uses. They wanted him to describe some things from different lab reports and ZMAX assignments, so very similar. Who
Yeah.
else has a question? Does your job require a clearance?
Mine does not.
Okay, was eligibility for a clearance something that this company asked about, just since you could move around in the company?
They didn't ask that for me, at least.
Just curious.
Yeah, they didn't ask that of me.
Who else has a question?
So you said submarine gyroscopes have 3 kilometer lines, as opposed to 150 and 200 meter lines that go into space.
Mhm.
So why do submarines require such more sensitive technologies?
That I do not know. That I do not know at all. I don't know if I'm allowed to know that. All I know is that we provide the gyroscopes, and then we give it off to another site which has a higher clearance than we do, and they work with the Navy specifically. So we're given, like um, the specs, but we kind of just hand it off and clean our hands of it, and we can only suspect what they're using it for, but I haven't asked, so I kind of want to know too. I want to see what my lead thinks.
If I had to guess, and since my job security doesn't depend on offending or not offending the people who keep that secret, but if I had to guess, it's probably two things. In space, you're talking about larger distances overall. And also on there's I can think of two very different reasons why you might need much more precise navigation in the ocean. For starters, there's a lot more things that you can hit. A friend of mine who served on a submarine told me something about how in training they were all hit over the head with some lessons from a submarine that had collided with an underwater mountain. There are mountains underwater, and there's a lot more at stake from being in the wrong position. The other thing is that one hears stories of submarines going to very interesting places on the ocean floor where governments and companies might have put very interesting things for very interesting reasons. And they try to get at them through small ports. And let's face it, you can't really at that depth have a diver out there. So you got to be right on top of the thing so that you can manipulate the robot arm. Being off by even a few meters might make it impossible. So that would be my guess, that some of it is for navigating very close to very interesting things, and some of it is for steering far away from very dangerous things like underwater mountains. In space, there just isn't as much stuff and precision. Just a guess, though. Who else has a question?
I have a question. I have two questions actually. The first one, do you prefer pancakes or waffles?
What game are you playing?
And okay. Serious note. So let's say I want to apply to Northrop Grumman, right? And I don't have much of industry experience, right, on my resume. What are some of the things I can focus on that in a way substitute for professional experience or industry experience? Do you recommend like more projects, like personal projects or personal research and stuff like that?
So for the first question, I prefer waffles. For the second, the funny thing is that I actually tricked my recruiter into thinking I had 2 years of industry experience. And that was mostly because I had a lot of research, had a large background in research, and I was pretty involved in college. I was a part of like the student telescope operator thing. I was a learning assistant, and I was involved in 3 different research groups. So I had a lot to talk about, I guess, on my resume when it came to like the interviews. Of course, they just focused on fiber optics, that whole background. But yeah, I would just say being involved in in outreach opportunities and being involved in different projects is really helpful.
What was the, I know you had some job in the Bay Area right after college.
It didn't line up.
Oh.
So I interviewed for BioHub, which was like a research initiative between Stanford, UCSF, and UC Berkeley. And I would say their interview was pretty similar to Northrop's as well, where they had me read papers and explain what I learned from them, what was the takeaway of those 3 papers that they gave me. And they had me go on the whiteboard and explain what PCR was in biology. So that was that experience.
I think some of Kenneth's question may have been aimed at if one hasn't done an internship, but one decides to spend some time during the summer learning SQL or learning how to do something with like a Raspberry Pi or an Arduino or whatever, how would you take a personal project like that and make it work on a resume or make it work in an interview?
I mean, essentially you're delivering a project, right? So you're starting it from the ground up. You started by procuring parts, developing a plan of action, and so I'm also a part at work of this high school involvement program. So I work with a high school students so that their application looks better to colleges. So we help them develop a project. Right now, I'm working with a high school student whose project is to use a Raspberry Pi with a fingerprint scanner. And essentially, what she wants to do is do a 2-step authentication program with a fingerprint scanner and send an email with a specific code so that the encrypted file can be open. And so I think that in itself is marketable, right? Because you came up with an idea, and while yes, there's resources online, you can change it a little bit, make it a little bit more, make it difficult, or change an aspect about it that's not found online, and deliver it in the same manner as like a research project, right? Because research is the same thing. You're given a project and you're expected to create a deliverable code or device or whatever.
So in other words, if someone wants to take a summer when they didn't get an internship and mess around with a programming language or an electronics kit or whatever, don't just say, oh, well, I messed around with it, but have a goal. Say, I'm going to write a program to do this, or I'm going to build a device to do that, and then show the steps you took to get there.
Yeah.
Okay. Someone else must have a question. What are some directions you could see yourself going in, like as a next step at Northrop or in the wider industry?
So I would like to continue in the technical path. I could go into a machine learning group. I could go into being a manager, but I kind of see myself being still in the experimental realm of things, and continuing in the technical path. Um, but there is a lot of opportunity to move on and do something different, move on to just programming, move on to a manager position. Um, but personally, I want to remain in the technical path that I'm on.
When you say technical as opposed, you contrasted, I think we all understand the contrast between technical and management, but you contrasted technical with machine learning, which someone would think, well, it's still technical, it's technology. So I assume you mean more hands-on versus coding?
Yeah, that's what I meant. Mhm.
Okay. And how did you find out about this job?
Honestly, Sarah Margala told me to apply to Northrop, and she just said to go on the website. It's really, really simple. They have um, they have a little section that's for early career and internships. So you could be a college student and work at Northrop as well. And I pretty much just looked at their engineering positions that they had available.
And it's, yeah, Sarah, for those of you who caught that reference, was one of the panelists a couple months ago at the February alumni panel, and she's at a Northrop affiliated company in Connecticut. Who are the other alumni at Northrop that you're connected with?
There's Nicholas Cordoba.
Oh, that's right.
Um, there's one other person that I know of but didn't go in physics. I think he was mechanical engineering, and his name's Jonathan Alvarez or something. I think those are the main people that I talked to.
The Northrop facility up in Lancaster and Palmdale, they have been throwing a ton of money at Cal Poly Pomona, and most of it is at the engineering school. But still, in general, there are a lot of people in Northrop who have a positive impression of Cal Poly graduates. So even if you're not in the engineering school, it's a name they know. There are people there who know us. So it's definitely any company that's willing to throw money at any part of the university is a company that everyone in the university should be looking at for a career. Who else has a question? Somebody must, someone who hasn't chimed in yet. Or does anybody want to ask a second question? Those who already went?
Yeah, actually.
Sure.
So for the terms that you used, role, pitch, and yaw, I've never heard of them, but did you learn them on the job? Things. Oh, okay. So
Oh,
it
yeah.
wasn't like
I
something
had
that they
no
required.
idea what that was. Yeah. Yep. As soon as they like throw out acronyms all the time, and I'm just every meeting I'm like, whoa, what is an FTE? What is what are these things that you're saying? So there's a lot of different jargon that you'll just kind of learn on the job. And I think as an early career hire, they don't really expect you to know everything. So they definitely know there's going to be a learning curve. And so ask away.
That's
If
encouraging. Thank you.
Yeah.
you're at a stage where ignorance is expected, take full advantage of it. I mean, one thing that I see, especially at conferences, is that people are very, very, very receptive to students not knowing things. Students who ask questions, oh, you're a student, of course you wouldn't know that. And take full advantage of that. Who else has a question? Have you thought about going for any additional education? I know Northrop has good continuing education benefits.
Yeah, I have. I took a break because I didn't know where or what I wanted to study for graduate school. And so now I kind of know I don't really want to go into engineering, definitely not manufacturing engineering. Um, I just think I'm not really interested in process control management, which is what what they do a lot of. And I kind of miss physics. So I'm kind of thinking about going back for physics.
Okay, have you thought about particular programs or subfields or whatever?
I haven't.
Would you think of going part-time with Northrop paying for it, or would you try to go full-time to make a career change? Make a change of path?
I think I would do part-time, um, but still am leaving the door open for a career change. Um, and I think what I enjoy most about optics is that it's applicable in any field. It's applicable in imaging, it's applicable in, I mean, I can literally, there's a lot. So,
Well, I know that a lot of people go to Arizona's online program part-time. I think Sarah's doing Arizona right now.
yeah, she is. Yeah.
That's a really good program. Anyone else? Because I'm running out of questions here.
Yeah, I have another question. Wait, oh, sorry, did someone wanted to
Go for it.
go? Okay, I promise it's not pancake related, although I do prefer waffles too. So, you mentioned that you brought like ZMAX code and projects, and from, I believe you said the Advanced Instrumentation Lab. Um, were you referring to the advanced lab? I forgot the full, I guess, title of that course, but I believe there was like two advanced lab, I guess, and then one of them was I haven't taken it, so I'm just, I guess, eyeballing it, but one of them was like more on the electronic side, and the other one was more on like I guess like quantumy and like stuff like that. um so though from those two classes, the like applied optics and the advanced instrumentation lab, did you bring any other lab reports or other stuff from other labs, I guess, or were those two like your main, I guess, selling point?
I think those were my two main selling points, but I have used other labs for guidance. I think I've used, oh man, it was 234 for me, but I don't remember what that class.
2530 is no. Was which experiment did you use?
I think we were measuring the speed of light, whichever class that was.
Yeah, that's a really good experiment, because that one is using a lot of techniques that people would still use in more advanced research. Oh, I see some questions in the chat. Madison asked, how often do you have to travel for work?
So because of the pandemic, I haven't traveled much, but there are plans to have me go to Woodland Hills and watch a process being done. We've also talked about me going to, I think there's a site in Virginia where they want me to go see some crystals being formed at one of our subsidiaries. And so there's a little bit of travel for me, but not much.
if you go to Woodland Hills and you happen to have a little bit of time on your trip, let me know. We'd love to have you come talk to a class in person once we're back to in person.
Yeah, yeah.
Does anybody else have a question? If you don't want to speak up, you can put it into the chat box. But just go ahead and chime in if you want. Well, we will be back to in-person things at least somewhat this fall and hopefully 100% in spring. So at some point we will definitely have you out for an alumni career panel.
Yay.
Oh, actually, I have one more question. Besides talking about, you already mentioned a lot of research experiences and internships. What about extracurricular activities, student clubs and stuff? What have you found useful from that for your career?
So I didn't really participate in clubs.
You did the telescopes thing.
Oh yeah, I did. Yeah. So that was helpful to bring up because there was a question that they asked me in the interview, if I've taught or have interest in outreach, because at least at our site, we have a lot of, they're called ERGs, which are employee or engagement research groups. So we've got a club for running, cycling. I don't remember what that one paddle game is called. We've got a group for NG Women in STEM. So we're really well known for having a large community and having groups at our site. So they definitely asked me about that in the interviews. And I remember bringing up the student telescope group and visiting schools in the LA County. I think I also did like a IEEE introduce a girl to optics week, and I participated in that. And I remember talking about that experience of organizing an event and creating like permission slips to have high school students come onto campus with their parents, so that we could show them around the research lab and perform different, or I guess teach about different optical phenomena. So that's also something that you could talk about in an interview.
I think anything that involves teaching or working with less experienced people could provide some anecdotes for when they start asking about interpersonal matters and how you handle difficult things, helping someone. So yeah, that's a good point.
Mhm.
All right. I'm not seeing any other questions, so I'm just going to thank you again for coming, and I really hope we can do something like this in person at a future alumni event.
Yeah, I hope
Thank
so
you
as
for your time.
well. Thanks for inviting me.
Glad to do so. All right, everyone, we're done. Have a good weekend. We will pick up with point spread functions on Tuesday. Good night.
Bye.
Bye.